Hello. In this video, I'm going to walk you through the solution to the problem you were working on. Do the following functions have a horizontal tangent line on the specified interval? Well, there's a lot of functions here, but I'll do a couple of them. So let's look at that first one. We'll call that one number 1. If we find the derivative, horizontal tangent line comes from the derivative, so we find the derivative, which is 2x minus 2. Okay, so that will be equal to, I guess if I wanted this equal to 0, I could factor out a 2. X minus 2 equals 0. Well, I guess that would just give me x equal to 2. And that's definitely in the domain, so yes. It seems to work for this first one. We could try a more complicated one. Let's look at maybe, number 4 looks pretty complicated. Let's see if it works there. So we find the derivative, low d high, so 2x plus 3. Gonna need a little more space here. Less high d low. Over the denominator squared we go. So we're going to want to simplify to eventually find where this thing equals to 0. So we're going to get the following. If we expand in the top, we'll get 2x squared plus 3x, and then minus x squared minus 3x minus 2. So those will cancel. We can subtract the x squareds to give me x squared minus 2. So that'll be a difference of squares, x minus root 2, x plus root 2. And so therefore we get x equal to root 2 and x equal to negative root 2. Now x equal to root 2 we've got to reject, because if we look back over here, the domain was minus 2 to minus 1. So the positive number is gone, but minus root 2, that's negative 1.4. So that one we get to include. And so definitely this seems to happen as well on this problem. And if you look at all of the other ones, as long as you take your time and are very patient, you should find that they all have horizontal tangent lines. So you might think then, I guess every graph seems to have a horizontal tangent line. That would be kind of cool. Maybe that's a universal property of graphs. Maybe every graph always has a horizontal tangent line. But let's look at the extension here. Does this happen with every function? Well, let's try that first one. This is number 1. F prime of x will be equal to 2x minus 2. Okay, but the interval is 2 to 4, so if we set this equal to 0, we get x minus 1 equals 0, so x equals 1. So it seems like it had a derivative of 0, but this is not part of the interval. So we have to reject it. And so it seems like, no, this one does not have a derivative of 0. If you try the next one and the next one, you're going to find that these never have derivatives of 0, which means that it's not going to be always true. It doesn't seem like this is a universal property. Clearly there are some functions where this doesn't happen. So what's the reason? What's going on? Why does it happen in the other ones, and why doesn't it happen in these ones? And in particular, we need to look at, and I'll show you that first function, we need to look at something happening at the end points of the function. So what are the precise conditions? Well, if we look back at that first function, we had the following. So fx was equal to x squared minus 2x minus 8. And this is on the interval negative 1 to 3. Now, just for fun, I'm going to find f of negative 1. That'll be negative 1 squared minus 2 times negative 1 minus 8. Okay, well that'll be 1 plus 2 minus 8. So that will give me overall negative 5. Now what do you think you're going to get for f of 3? Well, you'll get 3 squared, 2 times 3 minus 8. So that'll be 9 minus 6 minus 8. Well, 9 minus 6 will be 3, subtract 8. Oh, look, negative 5. These are the same. And if you go back and look at all the other 4 examples, all of the functions have the same value at the endpoints. Interesting, interesting. Now, we need to look at some of the other examples in 2 and 3 because maybe did that happen in the other ones? Well, for our function we had, f of x equal to 1 over x squared. The interval was -1 to 1. And just if you would have tried, right, the derivative of this, if you simplify, will be -2 over x cubed. That's certainly never going to be 0 because the numerator, -2, will never be 0. But if you try to find f of -1, you're going to get 1 over -1 squared, which equals 1. And if you do f of 1, you get 1 over 1 squared, which is still 1. These are the same. So wait a minute. These are the same, but we're not getting a derivative of 0. What's going on here? What's different about the first function than the second function? And let's also look at the other one we had. We had f of x equal to absolute value x. Well, this was on the interval also, -1 to 1. And so f of -1 is clearly going to be 1. And f of 1 is clearly going to be 1. These are the same. But you're never getting a derivative of 0 from this graph. It's just that v. That's never got a horizontal tangent line. It has a critical number, sure, but not a horizontal tangent line, not a derivative of 0. And so what's wrong with these two graphs? And in particular, if you notice, the picture probably gives it away if we were to draw this one here. This is a swoosh graph, and this one looks like this. Well, I guess maybe we shouldn't have the arrows on them, but these are just their general graphs. And so if you look right here, we have this asymptote. And so this graph is not continuous. And this graph, it's got that point where the derivative is not defined. And so this is not differentiable. But if you look back, and you can try on Desmos, if you look at the original 5 functions, not only were the endpoints the same, but they were also continuous and differentiable. They were connected and they were smooth. And so what it seems like we need to have the derivative give me 0 every time, we need the following conditions. 1, we must have equal endpoints. Right? F of A must equal F of B. 2, it must be continuous. And 3, it must be differentiable. And if you imagine, try drawing a graph that starts and ends at the same point, the same y value. Imagine it being continuous. Imagine it being differentiable. How in the world would you draw a graph like that that doesn't have a horizontal tangent line? I don't think you could do it. You take those 2 points, no matter what you try to do, you're going to end up, in this case, we've got 2 horizontal tangent lines, one there and one there. And this is indeed a theorem, which we're going to look at in the next video. If you have equal endpoints, if you have a continuous function, and if it is differentiable, then it guarantees that there will be some point along the way where the derivative is 0. So hopefully you enjoyed watching this and enjoyed solving the problem. We'll look at the proof of this and the theorem, which is called Rolle's theorem, in the next video. Thanks for watching.